All right, let's dive straight into this. Welcome to our explainer of the Cambridge source material. Today, we're opening up the absolute ultimate math toolbox for conquering right-angled triangles. Look, if you're gearing up for your Cambridge IGCSE Mathematics exams, specifically the 0580 syllabus, you have definitely stared down some seriously intimidating geometry problems. But here is the secret. Beneath all those chaotic diagrams and confusing scenarios, the math is actually remarkably predictable. Today, we're going to totally transform how you look at these problems, giving you a foolproof, step-by-step system to navigate Pythagoras and trigonometry without breaking a single drop of sweat. We've got a really clear roadmap for this explainer. We are covering 1. The geometry challenge, 2. The Pythagoras foundation, 3. Labeling your triangle, 4. The trigonometric ratios, and 5. Choosing the right ratio. Section 1. The geometry challenge. Let's start with the exact kind of question that usually makes students panic the second they turn the page. Okay, when you first look at a boat trip problem like this, it seems completely overwhelming, right? Just imagine it. A boat sets off from point S, travels due north to point B for 6 kilometers, turns due east to point C for another 6 kilometers, and then, out of nowhere, pivots on a bearing of 135 degrees towards point D for 13 kilometers. Then the exam asks you to calculate the exact distance back to the start. It honestly sounds like a navigational nightmare. But wait, there's a massive secret to simplifying all of this. And here it is. Every single complex geometry problem just breaks down into simple right-angle triangles. That's the crucial takeaway. You don't solve this massive boat problem all at once. No way. You just draw lines to draw perpendiculars, creating perfect, neat 90-degree corners. Once you do that, what looked like a totally random zigzag across the ocean suddenly becomes a super manageable stack of right-angle triangles. And the best part, once we have right-angle triangles, we have total control. Moving on to Section 2, the Pythagoras foundation. Our very first tool is one you probably already know, but we really need to understand exactly when to use it. This right here brilliantly illustrates the pivot in our whole strategy. Side A is Pythagoras. It is purely about distance. If an exam question gives you 2 side lengths of a right-angled triangle and just asks for the third, you use Pythagoras. Full stop, done. But look at side B. The absolute second a specific angle is introduced into the mix, or if you're asked to go find an angle, Pythagoras has to go right back in the toolbox. We then need our trigonometric ratios. Knowing this exact boundary is literally half the battle. Let's look at how we actually apply this Pythagorean foundation in a real scenario, like a scale model garage. If we want to find the true slant length of the roof, we just break it down into 3 simple steps. First, identify your known straight sides forming that 90-degree angle, say the half width of the roof and the vertical height to the apex. Step 2, you square both of those numbers and add them together. Step 3, just find the square root of that total. Boom. That gives us our hypotenuse, the slanted side of the roof. It's elegant, it's fast, and it works every single time as long as we're only dealing with sides. Section 3, labeling your triangle. Because what happens when we do need those new tools because an angle is involved? Well, before doing any actual math, you absolutely must anchor your triangle. Your very first move, always, is to locate the right angle, that 90-degree corner, and look directly across the triangle from it. That side is the hypotenuse. Its position never ever changes. It is the longest side, and honestly, it's the boss of the triangle. Lock it down first, always. Now, this is where it gets kind of wild. The opposite and adjacent sides, they completely swap depending on which angle you're currently looking at. Think of your chosen angle as a giant eyeball. If the eyeball is up at the top of the triangle looking down, the side all the way at the bottom is the opposite, and the side right next to the eyeball, that's the adjacent. But if you move your eyeball down to the bottom corner, suddenly that vertical side all the way across the triangle becomes the opposite. The names are entirely dependent on where you're standing. Section 4, the trigonometric ratios. Let's get into the heavy hitters. Once our sides are perfectly labeled, we can pull out our 3 specialized tools: tangent, sine, and cosine. These are really just ratios, fractions that describe the relationship between sides for a given angle. Let's start with tangent, or tan on your calculator. This is your go-to tool when you don't know and honestly don't care about the hypotenuse. It purely connects the opposite side and the adjacent side. Let's walk through a worked example together where we need to find a missing angle. Let's call it x. We look at our triangle and identify our opposite side is 4 centimeters and our adjacent side is 5 centimeters. Okay, step 1, we write our equation. Tan x equals 4 divided by 5. Step 2 is where the magic happens. To get x totally by itself, we have to move tan to the other side using the inverse tangent function on your calculator. You'll usually see it written as tan to the power of -1. So we just type in inverse tan of 4 over 5, and just like that, we find our missing angle is 38.7 degrees. Notice how we rounded that to 1 decimal place? That is the standard Cambridge requirement for angles, unless the question specifically tells you otherwise. Keep that in mind. Next up in our toolbox is sine, or sin. This ratio connects the opposite side directly to our longest side, the hypotenuse. You're going to use sine when the opposite and the hypotenuse are the main players in your problem, meaning they are either the information you already have or the exact information you are trying to find. Let's look at another example. Here, we know our angle is 18 degrees, our opposite side is 11, and we're trying to find the hypotenuse, which we'll label Q. Step 1, write it out. Sine 18 degrees equals 11 over Q. Now, step 2 is a super crucial algebraic maneuver. When your unknown variable is stuck on the bottom of the fraction like this, you just swap it with the ratio on the other side. So Q equals 11 divided by sine 18. Step 3, punch that into the calculator, and we get 35.6 centimeters, rounded to 3 significant figures. Finally, we have cosine, or cos. This is the absolute perfect tool when your knowns and unknowns are the adjacent side and the hypotenuse. Let's see this one in action. We have an angle of 62 degrees, an adjacent side of z, and a hypotenuse of 20. Step 1, cos 62 degrees equals z over 20. If you already guessed we needed cosine here, you're absolutely right. And since our unknown z is on the top of the fraction this time, the algebra is so much easier. Step 2, we just multiply both sides by 20. Step 3, 20 multiplied by cos 62 gives us a final side length of 9.39 centimeters. Simple as that. Section 5. Choosing the right ratio. Having these tools is fantastic, but knowing which one to pull out under intense exam time pressure, that is everything. So here is your ultimate cheat sheet. You've probably heard of it, but seriously, you need to write it at the top of your exam paper the very moment the timer starts. SOHCHAHTOA. It perfectly matches your knowns and unknowns to the exact right formula. SOH, sine is opposite over hypotenuse. CAH, cosine is adjacent over hypotenuse. TOA, tangent is opposite over adjacent. Just identify what sides you have, identify what sides you need, and see which 3 letters match your situation. It's foolproof. Let's look at how this applies to a really tough word problem. We have a small tree that's 7 meters tall, and a taller tree. The distance between the top of the small tree and the base of the tall tree is 15 meters. The distance between the top of the tall tree and the base of the small tree is 20 meters. It looks completely chaotic. But by drawing horizontal lines to create right-angled triangles right there between the trees, identifying your hypotenuses and matching your sides using SOHCAHTOA, you can systematically calculate the exact height of that taller tree without panicking. Which brings us to a pretty fascinating conclusion. Just think about the sheer power of what we just covered today. If you have just one single measured side and one correct angle, you can use these exact ratios to unlock every single other dimension. You could mathematically build an entire scale model garage, or accurately navigate a boat across a massive ocean, starting from practically nothing. With trigonometry correctly sorted in your mental toolbox, you are unstoppable. You have the formulas, you have the labels, and you have the strategy. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Take these tools, apply them to your past papers, and ask yourself, what are you going to calculate next?